Welcome back, Chemistry Theory. This is the third video. So we'll look at other examples here involving the use of acid-base indicators and ones that will work versus ones that won't. If we look at this first example, so first of all, it's a low pH. So we know this. We're starting off with an acid. So it's like saying we have an acid here, and we're going to add base to it because the pH is rising. Now, the pH here isn't really low, so that tells us that it's a weak acid. And of course, the base here is relatively high pH, so it's strong base. So here we have a weak acid titrated with a strong base. We can see here that it changes here. So anywhere, if I look at where this vertical line is, it's approximately close to 8, so around 7.8, and it's close to 11, maybe say 10.8. So over here it was chosen that a suitable indicator needs to fall in this range. So what changes in between 7.8 and 10.8? So if we go back to here, and of course this chart is on your reference sheet, so 7.8 to 10.8, what changes color? Well, thymo blue changes color in that region. Also phenolphthalein changes in that region. So phenolphthalein was chosen for this region here. So that would work. That would change at the right region we need it to change at. If I look over here, which one that won't work? So over here, methyl red. Methyl red. Would methyl red change in between 7.8 and 10.8? Methyl red, 7.8. So here's 7.8 here. But yeah, we can see that it changes way sooner than that. It changes in between 4 and 6. And in between 4 and 6 is not in this vertical range, so we can't use that one. If I look at vice versa here, you can see we have a weak base because it's in the basic region, but it's not at 13 or 14. Strong, and then over here you can see we have a strong acid. So we're starting with a base, and we're adding acid to it. Okay, and over here, phenolphthalein, of course, would not be good because it changes in this 8 to 12 region, whereas the region we need is kind of between 4 and 7. In between 4 and 7. So if I'm looking over here, in between 4 and 7-ish, 4 and 7. So let's take a what. So this one, methyl orange lilac, wouldn't be the greatest. Methyl red is perfect though, because it goes from red to yellow in that range. Bromothionyl blue, maybe it would be close to going from yellow to blue in their area. But it looks like methyl red would likely be the best. And if you look over here, methyl red is the one that was chosen because it changes perfectly in that 4 to 7 range. Over here, of course, phenolphthalein. If I want something in between 4 and 7, phenolphthalein changes in between 8 and 10. So that's definitely not one that I should use. All right, so those are a couple of examples of good and bad indicators that you could use. If you look at the final page here, we'll look at, okay, so the equivalence point, looking at when is neutralization. We'll do a couple of calculations involving that. So problems involving night titrations. So it says here in a titration, 33.21 milliliters of 0.3020 rubidium hydroxide solution is required. So in the burette here, I would have my rubidium hydroxide. So that's my base. And I'm taking that and I'm adding it to the acid here, which is hydrofluoric. So over here, I know what the concentration of this is, and I know how much I used to neutralize. Over here in my acid, I know that I have 20 mils of it, but I don't know the concentration. And in fact, this is what we're figuring out here. Figuring out what is the molar concentration of the hydrofluoric acid solution. So what we have to do here first is write down the balanced equation. So hydrofluoric acid and rubidium, see it's a group 1 metal, so it's nice here, it's 1 to 1. And if we look at what we get here as a result, rubidium and fluoride. So rubidium is +1, fluoride's -1. So as we can see, it comes together easily. So it's a 1-to-1 here, rubidium and fluoride. So RBF, and of course H and OH makes water. So aqueous, aqueous. So this is a nice one because it's a 1-to-1 relationship. I think the one in the assignment I give you is a 1-to-2 relationship. So you have to be sure you balance the chemical equation right. So what we're told here, we were told that, so rubidium hydroxide has a concentration of 0.3020 molar, and the volume, 33.21 mils. We're going to have to change it into liters. So divided by 1,000 or move the decimal 3 places to the left, and we get that. Hydrofluoric acid, we don't know the concentration, but we do know that we started off with 20 mils of it, which is 0.02000 liters. So the scheme that we're going to be using here, we know this, so with this we can figure out moles by using C equals N over V. And then of course 1-to-1, we can go from 1 moles of rubidium hydroxide to moles of hydrofluoric acid, and then we can do this. So we're going to be using 3 steps here. Kind of a stoichiometric problem here. So first of all, let's figure out moles of rubidium hydroxide. Moles of rubidium hydroxide. So we have this relationship that we used way back in physical science. We know what C is, we know what V is, so we could figure out N, the number of moles. So molar concentration, 0.3020, multiplied by my volume in liters. And that's going to give me this. And I'm not going to round off yet, just leave the number as that. So 0.0100294 moles of rubidium hydroxide. So now the next step we need to do is figure out, so I'm over here right now. So I figure out moles of rubidium hydroxide. Now I want to figure out moles of HF. Moles of HF, and it's relatively easy. So I start off with my moles of rubidium hydroxide. And I can see from the balanced equation, 1 mole requires 1 mole. So 1 mole of rubidium hydroxide requires 1 mole of HF. So of course we know that we're doing it right. And you can see here it doesn't change. Now that's why balancing the equation is good, because you can see this was an easy one. It's a 1-to-1. But if this had been 1-to-2 or 2-to-1, we'd have to reflect that over here. But for this one, since it's 1-to-1, we have the same amount here of HF. Then lastly, the concentration of HF. So earlier HF, molar concentration, square brackets is code for that. It tells us that we're looking for the concentration of HF. So C equals N over V. So over here we had C equals N over V for rubidium hydroxide. Now I do it over here. We know the volume, we know the moles, so we can figure out big C. So 0.0100294 over the volume of hydrofluoric acid that I have, 0.02000. And I get, let's see here, these are all 4 sig figs. So I'll write 4 sig figs. So 0.5015 molar of HF. All right, so maybe what we'll do is I'll get you to try this last one. We'll stop the video there. You try the last one, then we'll come back in the last video here to see how we do it.